Hi guys, so this is the tutorial for continuity of piecewise functions, and I am going to talk a lot about continuity, but I'm sneakily trying to get some extra practice in on piecewise functions because I sense that some people need practice. Before we start, please make sure that you have some scratch paper out. You're going to need it. And if you don't immediately recognize the three parent functions in this first example, that's a good indication that you need to stop, and before you watch this video, go to your CRAM account and practice the functions, just recognizing the functions, recognizing both their general shape and the particulars of their graph, because I'm going to reference that a ton in this video, and if you don't immediately recognize the shapes, it's going to be really frustrating. Great, so I assume you have scratch paper. Me too, my little sticky note. The instructions for this problem is to graph the function and then identify and explain its points of continuity and discontinuity. First step, graphing. When I do piecewise functions, if you remember my analogy from class, it's like a country where different parts of the country have different laws. And this first part of the piecewise function is the law you follow. In other words, this is the function rule. It tells you how to get the y value. This second part of your piecewise function is the boundary of the different regions. In other words, we're going to start with the back section and divide our country up, and then we're going to use the first section of the piecewise defined function to actually create the graph. I can see from these inequalities that my graph is going to have boundary lines at -2 and at +3. And I use boundary informally in this case. It's not a math term. I'm just trying to explain what I'm doing. These dotted lines are not part of the function. They're guides to help me draw the right shape. Now that I have the sections, I'm actually also going to go ahead and just write at the bottom a reminder to myself about which rule is going to be in which section so I don't accidentally get confused. The first rule is for the less than -2 section, which is right here, and the rule I'm going to follow is x plus 3, absolute value, minus 2, and that would be a y equals that in this section. I know from looking at this graph that that's going to be an absolute value shape. I don't know where it's positioned, so I may not see the whole V shape, but I'm sort of expecting that before I even go to graph it. Similarly, in the middle section, we're going to have y equals -x² plus 5, and I expect that to be quadratic. I know it's quadratic. In the last section, we have a natural logarithm function, so it would be y equals -ln of x minus 3. And it'll have a log shape. This is just my thinking process. You don't have to write it down, but I highly recommend it, at least for your first couple examples. Next step is to create the graph. There are a number of strategies to do this, and maybe one reason people get stuck is because you actually can't decide which strategy to use. Most commonly, you can either rely on the parent function and think about the transformation, or you can plug in x values. If I was going to plug in x values, I would always start with this boundary line just to get a sense for where this graph is going to be starting, and in particular where it's going to meet the next graph and the next piece. So if I start by plugging in -2 to this function, I would get work that looks something like this. I would get y equals, oh that's a bad pen, hang on. Y equals absolute value of -2 plus 3 minus 2. Order of operations, I do the inside first, so this is the absolute value of 1, and 1 minus 2 is -1. So that means this function has a point at -2, -1, and that's going to be right here. And then before I decide to shade that point in, I'm going to go back and check the inequality symbol. Since it has an equal to sign, I can go ahead and shade in that point, because that's a closed circle. Now I still need to draw the rest of the function. I'm going to switch strategies now. I didn't have to. Some of you may want to just plug in -3, -4, -5 and do the same work and just plot the points. I would like to think more big picture. And so I'm going to think for a second about the shape of the parent function here. And I'm going to do this on my scratch paper so that I can kind of rationalize for you. I know that the normal absolute value graph, the absolute value of x, looks like this. And not only do I know it has a v-shape, but I know particularly that the v-shape's vertex is at 0, 0, and that the slope is up 1 over 1, up 1 over 1, just like that. Well, this function is basically another v-shape, except this function has been shifted around. In particular, the number inside the absolute value is the h, and actually we have an h value of -3. Remember to flip the sign, that's algebra 2. And this h value tells me that my graph has moved left 3 units. In other words, this v goes over 1, 2, 3, like that, and then we draw it there. But that's not the only change. The number at the back also tells you that it's moved down 2 units, so this v also goes down. And this is the shape that I want to actually put on my graph. To be precise, the vertex of the v is at -2, -3. I'm sorry, I said that backwards. -3, -2, because that's your x value. So if I go over here to my graph, I go left 3 and down 2. And I know that that's the vertex of the graph, so without plugging in any more values, I'm going to go ahead and go up 1 over 1, up 1 over 1, up 1 over 1, and I get this V-shaped graph, just like this. And that's a really precise start to your function. Of course, I don't continue the graph past the dotted line, because this state ends here, and a different law is going to pick up in the middle. We can use the same strategies to graph the quadratic. I'm going to recognize, first of all, that this is a negative quadratic, so I expect it to be some sort of downward shaping parabola. Now, you might be a little confused about the plus 5. Does the plus 5 mean that my parabola has shifted to the right 5 or up 5? We have 2 options for what it could look like. If you don't know which one it is, I recommend plugging in points to check. The easiest point to check is kind of the 0 right here in the middle. If I plug in a 0 to this equation, 0 squared is 0, 0 plus 5 is 5, which means that 0, 5, this point right here, 1, 2, 3, 4, 5, is on my graph. That's a pretty good indication that this graph has been shifted up 5. Now, we want to be really careful on the boundary points, so don't just assume that you can draw your parabola and it'll turn out great. You need to go back and calculate at the boundary points where this line is going to hit the border. So I do that by plugging in -2 to this equation. It looks like this. I'm writing it out because I want you to be careful with your order of operations. -2 squared is 4. The negative times the positive 4 is -4, which gives me a positive 1. So at -2, we have a point at positive 1, and it's an open circle. Now, from here, it's okay to kind of guesstimate the middle, because you know what the shape is going to be and you know where it's going to end. If I came to the other side, at positive 3, I plug in positive 3, 3 cubed is 9, -9 plus 5 is -4, so I come down here, 1, 2, 3, 4, and another open circle right there. And again, it's okay to guesstimate the shape in the middle here, as long as you have the boundary points right. Last section is your natural logarithm. All right, same thing where we can use a combination of logic based on the parent function and plugging in points. I'll start with the parent function. I know that the natural logarithm looks like this. And I know that, to be exact, this has a vertical asymptote at 0, the normal ln function. And I also know that this point right here is the point 1, 0. That intersection point is exactly 1 unit over. This function has had 2 things done to it. The first is it's been shifted to the right 3 times. So if I imagine taking this function and shifting it to the right, we would go 1, 2, 3. The new point would happen right there. And in particular, the new asymptote would actually be at 3. Now, this is just the shift. The next thing that's been done to this logarithm is it's been reflected, And the negative out front means it's been reflected over the x-axis. So this shape, if you imagine flipping it over the axis, is going to turn into, I'll change colors here, it's going to turn into this shape. In other words, we'll have an asymptote at the top, and then the side will turn over. And that's the shape I want to put on my graph. Now, conveniently enough, the asymptote of the log is the same as the boundary, so that makes it really easy to draw. I start right up here at the edge, and then I cross at 4, and then I turn off to the side. Now, it won't always work out that your asymptote and your boundary line are the same. If it hadn't been the same, I would have had to calculate where this function is actually going to hit the boundary with its open or closed circle. Okay, this is your graph. Beautiful. What we need to do is identify the points of discontinuity. This you can do just based on what you see, because you've taken the time to make a really accurate picture. So here's what I see. I see a continuous function where all the points are connected, connected, connected until the point where x equals -2. And at x equals -2, this function has a jump discontinuity. And then after -2, we continue, everything's connected, no problem, until we get to +3. And at 3, we have, you could call it infinite or jump, I don't really care either way, but it has a non-removable discontinuity. The last thing we need to do is figure out where the function is continuous. And when we say continuity, we really want to list all of the other points. So interval notation is the best way to do that because there's just a zillion points where it's continuous. When we use interval notation, I want to describe everything except for these two numbers. So this is what the interval would look like. And ignore my typo there. Notice that this is different than the domain. Technically, -2 is in the domain of the function because there is a closed circle right there. 3 is not in the domain of the function, but -2 is. It's just that it's not continuous at -2. Cool. We're short on time, but I think it's worth doing one more, at least somewhat together. Take a look at this graph. I'm going to pause the video. When I come back, you should have graphed the boundary points for these 3 sections and set up the basic shapes for each one. Right, so this is all kind of my thought process. I've got my graph divided up. I expect these shapes to be part of my answer. Now it's time to start actually plugging in points. When you press play again, I'm going to show you the first part of the graph. Right, so the first part was a reciprocal function. Oh no, I drew it backwards. This negative up top should make it flipped. Hang on. Okay, so I'm leaving my mistake in because teachers make mistakes too, and because maybe that helped you realize a common mistake you made. The negative on top takes, this was a positive, and it takes the shape and flips it up and down. So actually, the 2 graphs should be on this side. Notice how I drew asymptotes, and I had to in this case because the asymptote didn't just line up with the boundary point. Great, we're going to pause again, and then we're going to look at the middle section. So the middle section is just a linear function, y-intercept, and slope. Let's do the last section. So for the last graph, your exponential decay graph isn't shifted around at all. We're just cutting off most of the shape and we only see the little tail. Now, I glossed over something, which is these boundary points. This boundary point actually connects the 2 pieces, but the only way you know that is if you actually take the time to plug it in. If you plug -3 into the first function, a -3 on the bottom here makes this -1 over +1, which is -1 plus 1, which is 0, which is why this point is right at 0. If I plug in -3 to this function, I also get 0, which is how I know that they connect. On this side, I just approximated where the shape should be, but I should have calculated, and what I would do is I would plug in +3 to e to the -x, and I would get e to the -3, which is the same thing as 1 over e cubed, and that's going to be a small decimal number. From there, I just approximate. Lastly, we identify discontinuities and regions of continuity. I'll add some practice problems to another video.